I'm Sai Ashish Somayajula, and I'm going to present my work, Generalizable and Stable Fine-Tuning of Pre-trained Language Models on Low-Resource Texts. Pre-trained language models have advanced NLP with significant improvements on various tasks. However, fine-tuning PLMs on low-resource text poses significant challenges. There is a high variance in performance across different final layer initializations for the same set of hyperparameters. They are prone to overfitting due to their large capacity, leading to poor generalization on test sets. Prior methods address this issue by encouraging proximity to pre-trained weights. Among these methods, fine-tuning a subnetwork selected based on the empirical Fisher information matrix is a promising direction, with improved results. As can be seen in this diagram, these methods choose a subnetwork indicated by the green edges based on the empirical FIM and only fine-tune these weights on the downstream task. The remaining weights denoted by the red edges are frozen pre-trained weights. That said, empirical FIM has some limitations in low-resource scenarios. Data scarcity can skew the gradients used to compute the FIM, leading to suboptimal subnetwork selection. Theoretical results claiming empirically determined FIM deviate significantly from the true FIM when the sample size is low. Thus, we propose a subnetwork selection method that deviates from the prior empirical FIM-based selection. But how do we choose an optimal subnetwork from among many options for a downstream task? We can choose the one that performs best on the validation set of the downstream task. Thus, it becomes a challenging combinatorial problem to select a subnetwork based on its performance on the downstream task. So there is a need for a computationally efficient approach to solve this challenging problem. We propose transitioning this problem into a continuous optimization of the subnetwork selection and task-specific weights based on the downstream task performance. That is, first given a subnetwork or a set of green edges, we learn those task-specific weights on the training dataset. We evaluate the learned network on a held-out validation set and update the subnetwork or the combinations of the red-green edges in the network graph. So how can we convert it? We first represent a subnetwork mathematically. Assume W are the task-specific weights and W0 are the pre-trained weights. Observe for a given subnetwork, the red edges can be written as 0 head-mod product W plus 1 head-mod product W0. And for the green edges, it can be written as 1 head-mod product W plus 0 head-mod product W0, where head-mod product means the element-wise multiplication operation. Motivated by this formulation, we propose the following attention-guided weight mix-up strategy. We represent the resultant weight as a linear interpolation of W0 and W. The mixing coefficient is denoted by alpha, referred to as attention parameter in this work. It determines the chosen subnetwork. If alpha is 1, then the corresponding weight belongs to the subnetwork to be fine-tuned. And if alpha is 0, then the corresponding weight is assigned to the frozen pre-trained weight. W depends on the chosen subnetwork, that is alpha. However, alpha is not just restricted to 0 or 1 in our formulation. It can take any continuous value in 0 and 1 range, making gradient-based optimization feasible. Since alpha ranges between 0 and 1, it facilitates a continuous relaxation of subnetwork selection, and the edges are depicted in the shades of green and red. If alpha is closer to 0, then the corresponding weight has more influence of the pre-trained weight and vice versa. With this formulation, the next objective is to learn the optimal alpha that influences the subnetwork and also the associated task-specific weights W. To learn alpha and W that improves the downstream task performance, we need a nuanced approach. Alpha and W are interdependent. Given a subnetwork determined by alpha, we learn W. So thus the learned W is an implicit function of alpha. We then evaluate the learned network characterized by W and update alpha to improve the overall performance. These objectives can be perfectly achieved using a bi-level optimization framework performed in 2 stages. First, let us describe the stage 1. Given a subnetwork determined by alpha, we learn W on the training split by minimizing its corresponding task-specific loss. We also add weight decay to W to enforce regularization. The learned W denoted as W star of alpha is an implicit function of alpha, since W is learned by minimizing the loss that is a function of alpha 2. In the second stage, we evaluate the network determined by W star of alpha on the validation split and update alpha. Weight decay on alpha encourages the alpha values to be close to 0, thereby encouraging a higher contribution from the pre-trained weights in the resultant weight representation. Clubbing the two stages together, we have the following bi-level optimization framework. As depicted in the diagram, the optimization is performed iteratively by computing the gradients of the loss function at each stage. Going into more details about the optimization algorithm, we use one-step gradient descent at each iteration, and finest difference approximation is used in the second stage to compute the gradients of W star of alpha, which is an implicit function of alpha, with respect to alpha. We next perform various experiments to validate the efficacy of our proposed method. Let's dwell into the experimental results. First, we compare our method with previous FIM-based subnetwork selection methods, specifically child tuning D and DPS-10s, focusing on low-resource scenarios with training data splits of 300, 500, and 1000. We report the average mean and standard deviation of evaluation metrics across 8 glue datasets. For each dataset, the evaluation is conducted over 10 random seeds. In the 300 data split setting, both child tuning D and DPS-10s underperform compared to the vanilla fine-tuning, underscoring the limitations of FIM. However, our method significantly outperforms these baselines. In the data split settings of 500 and 1000, our method not only surpasses vanilla fine-tuning, but also exceeds the performance of prior FIM-based methods by a significant margin. We also compare our method against parameter-efficient fine-tuning methods such as prompt tuning, prefix tuning, and LoRa in the 500 and 1000 training data split settings. We report the average performance across COLA, RTE, STSP, and MRPC. Our method significantly outperforms these baselines. It is important to note that the primary aim of these PEFT methods is not necessarily to surpass vanilla fine-tuning in low-resource settings. Instead, they are designed to achieve competitive performance without intensive resource utilization. In contrast, our method draws inspiration from regularization techniques such as child tuning D and DPS-10s, which are specifically aimed at reducing overfitting and enhancing performance in low-resource fine-tuning scenarios. We evaluated our method against vanilla fine-tuning across 5 PLMs, reporting the mean and standard deviation from 10 different runs. Our method demonstrated improved stability across various PLM architectures. Notably, with XLNet, we observed a significant performance gain of 8.48% over vanilla fine-tuning, accompanied by a significant reduction in standard deviation by 9.73. Additionally, while vanilla fine-tuning occasionally produced degenerate results with some initialization leading to poor performance and increased variance, an issue that is attributed to vanishing gradients, our method, using the same initializations and settings, yielded better outcomes and did not exhibit degenerate results. We compared our method with other regularization-based methods on 4 smaller datasets: COLA, RT, MRPC, and STSP. We report the mean and standard deviation from 10 runs for each comparison. Our method consistently surpassed all other baseline in terms of average scores, with a particular notable improvement on the COLA dataset, which highlights the effectiveness of our approach. Additionally, our method demonstrated the smallest standard deviation averaged over these datasets, indicating increased stability across different experimental settings. So with this, I would like to conclude our major contributions. We propose an attention-guided weights mix-up strategy that deviates from prior FIM-based subnetwork selection approaches. This new formulation allows for a continuous relaxation of subnetwork selection and task weights estimation. Additionally, we introduce a bi-level optimization framework to simultaneously optimize both W and alpha on different splits of the training dataset. Our approach consistently outperforms various baselines in low-resource scenarios. Our approach also demonstrates improved stability across different PLM architectures. Let us briefly dwell into our future works. Recognizing the potential of our method for continual learning, we plan to adapt and extend this method to address that important task. We can learn the task weights and attention parameters such that they retain the maximum old knowledge while adapting to the newer tasks. So with this, I would like to conclude my presentation and thank you.